Hey there, it's me, Miss B, and in this video we're looking at the Unit 3, Lesson 8, Cumulative Practice Problems. So let's look at this one first. This one says, or our first question says, this is an invalid proof. So first of all, it is an invalid proof, meaning it does not work. So it's an invalid proof that all isosceles triangles are similar. So we want to know which step is invalid, like which step did they do wrong? So it's invalid proof that they're all similar. Explain which is invalid and why. So let's read through it and then we'll kind of see what steps don't work. So first off, they say draw two isosceles triangles ABC and DEF, where AC is BC and DF is EF. All right, I'm going to sketch this along with them just because I can. So AC and BC. And then I'll draw another triangle here where we have F at the top, DF, and EF. Okay. Dilate triangle ABC to a new triangle using center C and scale factor of DF over AC. So they're saying DF over AC, that would be DF over AC. And we should always do image divided by pre-image. So that way we get our correct factor. And so that works. We would dilate it by that scale factor, and that would make them both the same size. So then A prime C and B prime C is DF and EF. Good. Those are all good so far. Oh, and I forgot to say that since these are isosceles, we should have like our congruence marks on those. Okay, so now translate by directed line segment CF to take A prime, B prime, C to a new triangle, A double prime, B double prime, F. So basically they're saying, hey, now that your triangle is the right size, let's move it over so that your top point here rests on the top point here. So we're translating it there. Good. Since A double prime F is equal to DF, we can rotate using center F. Yeah, because mine are drawn so they're in the same orientation, but they might not be. We just know now that C and F are going to be in the same place, so we might have to like swing our triangle into place so that things line up. So that's what this one is talking about here. It's saying translate by that line segment, and then ABF. So our distances would be the same, and then we would rotate using center F to take A double prime into the right spot. So steps 3 and 4 are both valid as well. So that just leaves either 5 or 6. So let's keep going and look through these ones. Since B double prime F is equal to EF, we can rotate using center F to take B double prime to E. Okay. Uh, mm, well, mm, Well, yeah, you can do that. You can rotate B double prime F to EF, and that would take B double prime to E. That's true. So, okay, now let's read step 6. We have now established a sequence of dilations, translations, and rotations that takes A to D, B to E, and C to F. So the triangles are similar. Well, they're going to have the same side lengths. We weren't given anything about angles, so we don't know anything else there. But step 6 is what I have a problem with because they're saying here, hey, this whole sequence now takes each of those points to each of those other points. But it is possible that I have some triangles that have a same length, and after the dilation, even though one of them might have the same length here, so I'll make another little copy of this guy. Let's see if I can show you what I mean. Copy. We'll paste it here. So if I had them exactly the same and I rotated around that top corner, then yes, it would swing them both into place. but nothing tells us about this bottom side here. So my isosceles triangle could actually be shorter like this. And in that case, I'm going to draw that version of this triangle actually. Yeah. So I'll draw that one in red and show you what I'm talking about. I'm going to draw a line here that is the same length as this blue one. And then I'm going to move it over and I'm going to use that so it'll actually line up. But now I'm going to rotate this. And I'll make another copy of it. So now we're going to copy it. And we'll paste it in. And I'm going to rotate it the other direction and kind of just make this isosceles, but have a much different angle. So now I have a triangle that when I do these transformations, I can line this piece up here. And I can say, ah, yes, when I rotate it, I can make the sides match up. So that's nice. But when I rotate it a second time, so this would maybe be after our first rotation where we take A to D, because that is the bottom left corner of each triangle. And now, once we rotate to take B over to E, or B double prime over to E, the result would look like this. So that's my problem with step 6, is that it claims something like this works. And while yes, steps 1 through 5 technically are correct, it doesn't mean that all of those points stay in the same place. So how are we going to describe this? We are going to say step 6 is incorrect, or we'll say invalid. That's what they wanted to know. Which one was invalid? So we'll say step 6 is invalid. Transformations affect, we're going to say transformations affect the entire shape. The other way you can describe this is that transformations affect the entire plane, which is just everything there. We'll say the entire figure. So when we rotate in step 5, it could move A double prime off of F. Because that's really the whole point, is like once we do that rotation, if we do another rotation, it's going to move the whole shape and they might not line up. So that's my explanation there. Or it's not A off of F, sorry. It's D. That was my bad. I just got my letters mixed up. F is the central point that we're rotating around. So move A off of D. Because we would never be able to make those two bottom corners of that isosceles match up unless we knew the angle measures were the same. So that is question 1. Let's look at question 2, a little less intense here. Which statement provides a valid justification for why all circles are similar? So they put it in bold. I'm going to underline it. That's what we're really looking at. Why are all circles considered similar? So some of these might make sense, but we want a valid justification. So when we say like justify your answer, that means use a mathematical explanation for it. So which one is a valid justification? All circles have the same shape, a circle, duh. So they must be similar. No, that's not mathematical. So we're not going to use that one. It is not a mathematical explanation for that or a valid justification. All circles have no angles and no sides, so they must be similar. Also, not a mathematical explanation. I am not really good with that one. option C says I can translate any circle exactly onto another, and so they must be similar. Well, if you can translate any circle exactly onto another, that's a rigid transformation, and that would be the definition of congruence. And I know not all circles are congruent to each other, but we're getting closer because we're using mathematical steps. So let's double check that D is correct. It says you can translate the center of any circle to the center of another. Agreed. And then dilate by an appropriate scale factor. So they must be similar. This is the correct explanation, is D. It's mathematical and it describes both of those things perfectly. For congruence, it's just the rigid ones, but we need the dilation part here in order to include similarity, which would account for having different size radii. Okay, so question 3, which pair of polygons is similar? Now we know for similarity, we have to have angles the same and our sides have to all be in proportion. So let's check these ones out. And it's only going to be A, B, C, or D. It is not all of them. So I might start with some here that are a little obvious by canceling things out. I'm going to cancel out B because these ones do not have right angles. While the sides are all like the same, the angles here are not right angles. So B is not going to work. I can also see a glaring error here on these two triangles. I have two sets of sides that are in proportion. These sides are half the length, but then I have sides that are the same, not by the same proportion, literally the same as each other, that are supposed to correspond. So they have different scale factors here. This one is using a scale factor of 1, and this is using a scale factor of 1/2. So not the same proportion. Okay, so let's look at our other two a little more closely. We want to make sure, and it does look like C is going to be our answer. We want to make sure we have right angles for everything. Angles are good. And then we do have a scale factor here of 2. And it looks like we do have a scale factor here of 2. And since this is a rectangle, we do have opposite sides being congruent. So all 4 sides work out. C is going to be the answer. But let's look at why A is not correct. So we have two different right triangles here. And while some of these pieces we might be able to put in proportion, they're not really going to work. So we're going to have sides that are longer than others. So like that 13 and the 5. These are the two longest parts. They are both the hypotenuse. So if we said 13 over 5, I'm going to use the larger shape here on the left as the one I'm starting with to just compare scale factors. We want to know, is that equal to, well, 13 over 5 would then mean the longer of the two legs would be the 12 and the 4. And then the shorter of the legs would be the 3 and the 5. Or in this case, the 5 and the 3. These are not proportions that are equal to each other. Because 12 over 4, this is 3. And the two next to it are not. So that's how we would know that one is incorrect. And so we just have C that is correct for this one. So that one took up a whole page because they wanted you to see those things, but let's move on to the next one. So number 4, we want to select all sequences of transformations that would show these are similar, and the length of AC, so I'm just going to mark that here, because I said the length of AC is 6 units, so I'm going to say this is 6, and I just kind of have it for myself there in red. Okay, now checking these out can be a little bit more difficult, but we will just double check here. Since these are different, or different sizes, I can actually kind of get rid of some options here. So I know that I'm going to need to do a dilation when my shapes are two different sizes. If I have 6, 4, and 8, I need to make that a 3, 2, and a 4. So it looks like I have a scale factor of either like 2 or 1/2 or something similar. Um, so I notice that option F here just kind of caught my eye. But option F, it says translate and then reflect. There is nothing about a dilation here. So it needs a dilation, meaning I cannot use F. Okay, so that's to start out. The rest of these have scale factors included in them. Let's look at what we've got. So it says dilate ABC using center A and a scale factor of 1/2. So I'm gonna just highlight so I know which triangles, just in case they give me some wonky scale factors, because sometimes they do that. So I have my green triangle, and then I'm gonna make this one down here blue, just so that I can double check which direction I'm going to. So ABC is my green. I'm gonna use that to help me with these. And I will color code this with AED being my blue one. Okay. So if I'm going from my green triangle to the blue one, I'm going to need a scale factor of 1/2. But if I'm applying my scale factor to the blue one to change it into the green one, my scale factor is going to be 2. So that might be something I'm looking out for here. So let's read. Dilate triangle ABC using center A. Okay, center A right here by a scale factor of 1/2. Okay, that'll shrink it down. It'll get closer. That's good. Then reflect over line AC. So they said reflect over this line here. Yep, that will work. I'm going to say that one works. Okay, now B says dilate AED. So we're dilating this one using center A with a scale factor of 2. So we're going to make this one get bigger. So this D should be taken to point C. So that's good. And then it says reflect over line AC. Yeah, they share that line, and yes, we do want to reflect over that, and that would take them onto each other. So this one works as well. So A and B so far. Okay. Oh, it actually looks like this next one is just reordering of A. So we're doing the reflection part first. We're taking AC, we're taking triangle ABC, the green one, and reflecting it over this line, and then dilating using a scale factor of 1/2, which is accurate. It would shrink it down to this size. So yeah, C works as well. So C works as well. I'm gonna make these a little neater instead of all scribbly. Okay, let's check out option D and then option E. So reflect triangle AED over line AC. So we're reflecting this over this line, and then we are dilating it by a scale factor of 2 to make it bigger. Yes. So again, that one is just reflecting it and then scale factor. So yeah, that one works. It's just kind of a reverse order for answer B. So let's look at option E, because we already canceled out option F. There was no dilation. This says translate triangle AED. I haven't used translations in my other ones, so translate AED by directed line segment DC. So that says take my little triangle here and translate it, meaning just shift it or move it so it lands here. So then I'm going to have like a triangle that looks like this. And then dilate using center C by a scale factor of 2. Well, that's just going to make it big again, but I would still have to do that reflection part, and that's missing. So this one is not going to work either. So I'll make a little note and say this one was missing reflection. And then for F, we were missing a dilation. And that's why we would not pick those. Okay, question 5. Determine if each statement must be true, could possibly be true, or definitely cannot be true. And then we want to explain or show our reasoning. Okay, two equilateral triangles are similar. Well, the answer to that one is it has to be. Because, so we would say must be true. Because it will be true for all equilateral triangles. They will have all sides equal. And all of the angles of an equilateral triangle are 60 degrees. So um, we would have, I guess, ASA triangle congruence here after a dilation. So um, we would say all angles are 60 degrees and um, can be dilated by a scale factor of, well, we can say an appropriate scale factor, but it's going to be of the two side lengths here. So of the original triangle and the second triangle. So this would be second triangle over first triangle to create um, equal sides. And that dilation is not going to change the angles at all, so that's nice. Oh, okay. Well, this one, B, says an equilateral triangle and a square are similar. Um, yeah, definitely cannot be true because they don't have the same number of sides. While all squares are going to be similar to each other and all equilateral triangles will be similar to each other, they're not going to be similar to one another. So, never true. They do not have the same number of sides. And that's it. Question 6 says find a sequence of rigid transformations and dilations that take square EFGH to square ABCD. So now we are going from this tiny blue square over to this one. On a previous question, they had us do this one to this one. I think that was actually from Unit 3, Lesson 6. They're just having us do the other direction now. So how would I describe this? Well, let's first translate. So we'll translate one of the points onto its corresponding point. We'll have to rotate to make sure things are in the right direction, and then we'll have to do a dilation. But let's also just check we don't have to do any reflections. I like to check by seeing what direction my letters go in. So A, B, C, D here is going counterclockwise. And I believe E, F, G, H, yep, it is also going counterclockwise. So I don't need to reflect anything. It's only when the order of the letters is going two opposite directions that we have to reflect in order to make them go the same direction. So I'm going to just do the couple steps that I had mentioned. I am going to translate. I am going to translate EFGH. We can say by a directed line segment, but I like to say so that. And you can choose whichever point you want to match up. So I'm going to say so that E coincides with A. You just have to use corresponding letters, so E and A correspond. Now I am going to rotate this into the correct position, and we're going to use the points that are already lined up now. So since E and A are lined up, we are going to rotate the image around point, we'll say point A, and E, F, G, H. It technically doesn't matter which direction you rotate, so I don't have to say clockwise or counterclockwise, and I don't have to include degrees here because we're just going to rotate until a certain point, although it does seem like the smallest direction of rotation here would be clockwise, so I'll just include that. I like to do the smallest rotation I need to do. So until, now we're going to say, I'm just going to use the second letters here, which are F and B. So we're going to say until F coincides. Actually, I should be saying F prime coincides with B. Because technically the image is now E prime, F prime, G prime, H prime. Our last step is going to be dilate. So dilate. Now this will be E, F, G, H. We'll just say dilate. Yeah, we'll just say E, F, G, H. Or we'll say the image. That'll be easier. Gets a little tricky with naming conventions. So dilate the image by scale factor. And now we actually have to calculate what our scale factor is. So that should be, it should be our image divided by our pre-image, or the fact that like we need our original multiplied by some sort of scale factor to equal 5. Divide both sides by 2. We're going to use 5 over 2. So dilate the image by scale factor 5 over 2 would be our last. Oh, and we want to use a center. I'm like, yeah, I have everything here. We need to tell you what center we're going to use. So, hmm, you know what? I actually made a mistake here as well. I should do my dilation first. So I'm going to switch some things around because I will not have it coincide with B. So I'm sorry, I made a mistake here. We're going to rotate the image afterwards. I need to dilate it first because then otherwise F is going to be way too short. So I have to change the order of these. So I'm sorry if you were writing this down with me or as I was doing it, but hopefully you're using pencil. Dilate the image by scale factor 5 over 2 using center E or center A. You know what? Let's use A. That's going to be more accurate. I feel like it's a little more, you know, teachers make mistakes too. So sorry if you were writing that down. We need to switch our order here because our shape would not be the correct size in order to rotate until F coincides with B because we would just be rotating forever and it would never actually touch if we did that as step 2. So we do need this to be steps 1 and then 2 and then steps 3. So that was my bad. The other way I could do this if I did the rotation first is I would actually have to tell you how many degrees. Um, and I don't have degrees marked on here, but I could like create an angle based on some of the letters, but that gets a little bit complicated, and I'd rather not do it that way. So much easier to get it to the right size and then swing it into position. So again, sorry about that one. That's number 6. Last one we have here is number 7, and then we're all done. So we want to select all true statements. Give given that angle AED is congruent to angle ABC. Now it doesn't actually say given that part on here, but it actually does say that on the solutions. So we're going to use that knowledge. Um, AED is congruent to ABC. Well, we actually don't even need that. If we have this line drawn here and we know that our pieces are in proportion with each other, which they are, we actually don't even need that statement. So you can do this without that written on here. So let's just select all true statements based on the figure that we're given. Angle ACB is 180 minus X. ACB, is that 180 minus X degrees? Nope, that is X degrees. So it's not going to be this first one. It is actually going to be the second one. It is X degrees because I do have sides here in proportion 5 versus 15 and 2 versus 6 give me a scale factor of 3. So they would just be the same degrees. Now they say triangle ACB is similar to ADE. So ACB is similar to ADE. That is going to be true because I have two sides and I have, well, all of these are in proportion. I have two angles actually and two different sides that are all in proportion here. And actually, if you have two angles, that's enough to prove it. The second angle that I have here beyond just the X is that I have A that's shared between them right here. Okay. So triangle ACB is similar to ADE. Absolutely. Yes, that is going to be true. They are going to be similar. Is AD equal to 1/3 of AC? So is AD equal to 1/3 of AC? Yes, because the small triangle is going to be 1/3 of the big one. That's the 2 versus the 6, and 5 versus 15, not 5 versus 10. We would have to include the entire side length here. So D is also correct. So B, C, and D. And then let's look at E. Is AD 1/2 of DC? Is AD 1/2 of DC? That will be true because AE is 1/2 of EB. It's really just cut into thirds. And so it's going to be cut into thirds down here as well. So just A is not going to be true here. B, C, D, and E for these ones. And then that is it because my next homework assignment is Unit 3, Lesson 9. So thank you for sticking with me through this one. This is the Unit 3, Lesson 8 cumulative practice problems for illustrative math geometry.